So welcome back to the channel. So today we're doing zero array transformation 3, which is um an update follow up from the zero array transformation 1 that we do 2 days ago. So if we look at the questions, now we have given a nums array and the queries where it's that which left and right inclusive. So we can decrement the value at each index in the range by at most 1. The amount by which the value is decremented can be choosing independently for each index, which means like if I give you the query from index 0 to 3, you can choose which one to apply. You don't have to apply to all of them, and then you just want to make the array to be a zero array, which every element is equal to 0. So you want to return the maximum number of elements that can be removed from queries. That means if we don't need the extra queries, then we can remove them. So we just want to know what's a minimum number that we can use, and then we return the maximum number of the queries that we can remove. If it is not possible to convert, then we want to return -1. So let's look at the first example. So given this nums is 202, and then we can query 0 to 2, 0 to 2, and 1 to 1. So in this case, we can remove 1, 1, right? Because when we apply 0 to 2, we can apply it to the first one and the last one. So this will be 1, 0, 1. And then we apply this again, then they all become 0. So the 0 array is fulfilled at this time, so we don't need to use this extra query. So we can return 1 in this case because we're not using that. So how do we gonna solve this problem? So this is the thing we talk about in the zero array transformation 1. We talk about using a diff array. We talk about using the prefix sum that we go in the 0 index and then change this to 1, and then when we go to index 2 plus 1, and then we do a -1. So this is still helpful here, and then we're still gonna use some concept from there. But in a high level, this is what I will do it. So we still need this different array, and then we still need the count because the count is just like the prefix, right? And then in this case, we use a heap instead. So what is the use of this heap? This heap is telling you that you have to keep track of the ending point because that's useful for us to know where it ends, and then we always want to use the longest one. As a greedily, if we have 0 to 3 and 0 to 2, we always want to use the longest one if that's the case. And sometimes we need to use both just because let's say we have this 202, right? So we're not eliminating duplicates, but we are just trying to find that if we have a longest one to use, then we essentially want to use that. Since the queries given is not sorted, so first step we want to sort these queries by the first index, like 0 index. Because when you use sort in Python, it's default to sort that, so you don't have to worry about it. So we want to use a max heap to keep track of the ending elements. So for this given example, we want to first go through each of the elements. So the idea here is we want to look at these elements, and then we want to go through the queries to see if they're still with the same index. So since this is sorted, this is what we want. So we will go into this and say, oh, okay, I need two queries at least to finish this, right? To reduce this to 0. So first I will go in here and check if the starting point, the left point, is the same as my index. If this is the same, then I want to add the ending point into my heap. So now my heap is 2. Since this is a max heap, so in Python, it's default to min heap, so you will need to do a negative, but just for simplicity, I would just say this is a max heap. It's 2. All right, and then since this is 0 index, so we move the j, so we can use a j to keep track of which one we access. So now we move this j to be here. So now we move up, means we already done processing the first query. So now we move up to here. So since this is the same index, same starting index, this is also 0. So we can also add this to the heap. All right, then we continue to move the j to the next one, and then we found this is not the same index anymore, then we don't ignore it. For this part, we then look at the count. So we can first count the different array, because we want to know what this different array is. And then we found this is actually 0. So we don't know how many things we have. So the next step is we want to go through the count. So first we want to compare the count with the nums at I. So since there's nothing in the different array, and then we add them, so we know that there's actually 0. So count is 0. We want this to be 2. So what we can do is we can go in and look at the heap. So if we have the heap and heap has something, we're trying to look at the first element. Is this larger or equals to I, which is the index 0? This is, right? Because this is representing the ending index. So we don't want it to be counted if this is not it is outside of the index, right? So since this is inside the array index range, so this 2 is greater than 0, so we see that at one of them. So we increase the count by 1, means in this array, in this index, we actually have some query that can remove this. So we plus 1 on this, and then we pop this out from the heap. And then we do this again, right? We do this again and say, hey, this is also greater than the index. So we pop this out, and then we plus 1. So whenever they're the same, we're done. Or like whenever the heap is nothing, then we get out as this for loop or while loop, right? And then at the end, we check. So if the count is less than the nums of I, means that you cannot achieve this, then you return -1. So the thing is, like, we want to check if there are enough queries to remove this. Let's say this is 2 and I only have 0, 2, and 1, 1. Then this only have 1 count. So means that either way, I cannot make this to be 0 index. And then now, since we're done processing this one, we can move on to this. But at the same time, I think one thing I missed is when you pop out the element, you also want to put a -1 on the next index. Sorry, I think it's this one. It means that whenever you got here, this count doesn't apply anymore. So count is just like a current prefix sum variables to keep track of the prefix sum. So whenever you hit the ending point, you want to -1. So when you enter a next loop, you essentially going through like the next element here, and then you just find out that because this is 0, it doesn't really matter, but you can also see that there's 1 pointing here. So you want to add this to the heap because they're the same. Then when you're done processing this, then you move the j next to the next one for the queries, so on and so on. I think I'm probably not the best in explaining these questions, but let's look at the code and see if this makes more sense. So first step, we want to sort the queries. So this will give you a sorted queries, and then the next step is we can initialize things like heap. We can initialize the diff array that we talked about, and then we can initialize the count. So for each of the elements, we can just call I in the range of the nums. All right. So our count will plus equals a diff array because we just want to see what is our current add up element for now, right? So what does this mean is like when you hit a -1 means that, oh, the query ended, so your count will be -=1, means that they're not, like, there are less queries that call to decrease the current index. So now we need a pointer, we need a element to keep track of which query we've done, right? So let's say our query is 0, 2, 0, 2, and 1, 1. So we want to know which one we have processed, and then the just variable only increase. It doesn't go back to the previous one. So I can't initialize in here because every time it will be a new one. So while j is less than the length of the queries, and we only care about it if the query starting point, right, the left point is equals to our, it's the same as our index. So we can add this to the heap, because by default this is a min heap. So you want to put a negative. Sorry, you want the j and the right pointer, and then you increase j by 1. And then we can process the heap. So while the count is less than the nums of I, and then there's a heap, and the heap first element on the top of the heap is greater or equals to our index. Since this is min heap, when max heap, we do a negative, so we want to take the negative back. Then we can increase our count by 1, and then we want to process the diff array, because when we pop up that, we're saying that, oh, this thing ends at its index, right? So we need to pop this up, and then +1 for the next index, and then minus equals to 1. And then as what we said, if the count is actually less than nums of at I, it wouldn't make it anyway, so just return -1 earlier. So indeed, what happens is like what is left inside the heap, right? So in this case, we'll see that later on we process this, and then we'll add 1 to the heap. And then since when you go through this, you have enough count, because count is not decreased. Count, I think it's -2 right here, but count is not getting decreased at index 2. Indeed, is being decreased at index 3. So when you go through the next thing, your count is still 2. So when you get to this 2, you said we have enough count, so we don't pop up anything from the heap anyways. So this is how it get there. Also, when we check the negative heap 0 greater or equals to I, this is not greater or equals to the index anymore. Means this query doesn't affect this index anymore, which is this line. So at the end, whatever left inside the heap will be the unused queries, because the used one will pop it out. So in this case, we just need to return the length of the heap, and then we can tell how many queries that we essentially not needed. All right, so this is the code, and then this is the solution. All right, so yeah, so when we need to the runtime, we need to sort the queries, and then we need to go through the nums array. So you can argue this is all of n plus m, because you have to go through the nums and the queries. But for m, you can also argue that you need to use m log m or m log whatever to sort the queries, and then the space complexity will be the heap, and also like the sorting algorithm based on what sorting algorithm you use.